I start off with a question. Why is SiC so important to the automotive market? Well, it's so important is because what we're seeing right now, today in 2020, 2019, is that we're seeing an inflection point in the automotive industry. And that inflection point is that we're seeing a decrease in the millions of units of ICE vehicles. So ICE stands for internal combustion engines versus electric vehicles. These electric vehicles are either hybrid or full battery electric vehicles. And what we see is that the market share of cars for electric vehicles is growing while the share is decreasing for regular combustion engines. And so we can see that in 2024, the market share will be about a quarter, right around 25% of electric vehicles versus 65% of combustion engines. And what makes this growth? Well, a lot of the growth comes from the electronics. It comes from the semiconductors, and the semiconductors and the applications on these vehicles include the inverter to drive the powertrain, and they include all the electronics like the onboard charger or the DC-DC inverter. And the parts that are going to be enabling these applications are wide bandgap devices. So you can see the growth rate from silicon carbide diodes, silicon carbide MOSFETs, and silicon carbide modules is all in the 40% growth versus silicon, which is well below that. So that's what's really driving the market for silicon carbide. Now I want to take a look at some of the enablers and challenges of the electric vehicle market. So some enablers are regulations. So every country is trying to reduce their CO2 emissions. So everybody, China, the United States, Europe, in all reducing this brings on an enablement for electric vehicles. Another thing that's enabling electric vehicles is the power semiconductor market. So according to Moore's law, over the course of history, our power semiconductors have gotten much more efficient, much smaller in terms of power density, and a lot lower RDS(on), which is your losses in your system. Some main challenges are the battery costs and recycling. So using the batteries ages them, and so aging batteries is an issue that needs to be solved. So there's a lot of research going into the battery portion of electric vehicles. The infrastructure, so charging, how many charging stations are we going to need compared to electric vehicles out driving around? And then you have residential charging versus freeway charging, and so there's a lot of unknowns going into the charging of the electric vehicles. And of course the resources. Similar to oil, the semiconductors use resources and those are not infinite. So we also need to be smart on how we're using our resources and how we're enabling these resources to make sure that we're not causing more harm. So this brings us to a couple goals for electrification. Some of that includes instantaneous torque, so that's an advantage of electric motors. Noise reduction, so you do not hear electric engines like you do combustion engines. We are working to lower the cost of ownership. So this goes on to how many miles you can drive and the cost to drive those miles. And then of course, for our environment, this is our CO2 emissions can be significantly reduced, converting all of our vehicles over to electric vehicles. So now I want to have an overview of the agenda for the remainder of this presentation for today. So we're going to take a look at ON Semiconductor's SiC ecosystem. So we do the devices, but we do a little bit more than just the devices. A big portion of that is our modeling. I believe our modeling is very unique and enables our customers to really start developing at a quicker and faster level. And then I'm going to dive into some of the solutions for electric vehicles. This will include the battery, or what's used to charge the battery for the onboard charger, the drive system, including the traction inverters, and then a little bit about the charging infrastructure. We'll end the webinar with a portfolio overview and some questions if we have time. So my first polling question is this: what would be your main reason for not purchasing a full electric vehicle today? Would it be the cost of electric vehicles, the range that the batteries offer, the infrastructure, to charge these things, the time it takes to charge electric vehicles, or is it something else like limited by options, either style and or the amount of vendors? When we go car shopping, typically we try to test drive a lot of different vehicles, and so it might be limiting to drive these vehicles. So we have about a minute to answer this question, and so I think it'd be very interesting to know with a broad audience what we get. So we have about 10 more seconds.
All right, thanks.
Go ahead, Matt.
Yeah, thanks, Brandon, for posing the question here. So the poll is closing just about now. We'll give a little bit more time just for everybody to finish submitting their responses, because I'm seeing some people are still in progress selecting their answer. But thanks for posing the question here. And if anyone out there has any questions on submitting responses to the polling questions we have later on in the webinar, you can also click on the help icon on the top menu bar, and the polling options should show up on the right side of your screen. So this poll just closed. For your question, what would be your main reason for not purchasing a full electric vehicle? It looks like about 32% of people are saying BEV cost, 18% say range, 20% say infrastructure, 17% say charging time, and then 6% say limited style and vendor options. So Brandon, what do you think about the responses?
Well, I think that it's very diverse. It looks like there's a lot of factors that go into it. So cost is definitely one. I know that with some of the new models out there, the cost is coming down. Infrastructure is something, and charging time is definitely something that needs to be addressed as well. So, but I'm surprised it's very mixed. So everybody has a different reason why or what they think needs to be improved. Thank you guys for your feedback. So now let's talk about the ecosystem of wide bandgap at ON Semiconductor. So we provide a very unique ecosystem focused around all of our solutions. So we have released to production SiC diodes that are really geared towards ruggedness. We have silicon carbide MOSFETs released that are geared towards ruggedness and speed. So one advantage of using wide bandgap is the speed benefits of these devices. We also have drivers that are designed to drive wide bandgap devices. Since silicon carbide uses a higher gate voltage to operate it, you need a driver that's designed to drive at those higher gate voltages. And then we also have a FIT design modeling for SiC and GaN power devices. FIT stands for Flexible Interface Technology. I believe that this is very unique to the market and gives us an advantage along with customers that are designing this, customers and users, a big advantage when they're designing these power systems. So I want to take a moment to walk through what the FIT is and how it can be very, very effective in design. So we provide a SPICE modeling. So it's very important to build a simulator that works across a bunch of different platforms. It reduces the amount of time that engineers have to work, and it provides very accurate answers. We believe that the models must be physically based, intuitive, and predictive. So what we do is we take a lot of our actual information and put them into our models. And then we have a bunch of different models and simulators that can be used. If you use one of our models, what do you expect to get on the output? Oh, before I go into that, I have another question. And my question is for our customers and engineers out there is, do you use modeling for new designs before testing them in the lab? So I'm wondering, yes, we typically test all new devices and model them first before we order them. No, we typically just order the parts and work through them on the bench and then see sometimes. So it depends on the design. If it's a new design, obviously there would be more time spent on modeling, or if it's an older design, you're just replacing parts, you might not need to. But I think it's very interesting because a lot of customers I talk to, some are very, very big on modeling, and they want to see this before they spend their resources doing measurements. And then I've talked to some that have zero really capability or zero interest in modeling, and they're just testing parts in the lab.
All right, Brandon, so I got the results from the poll that you just asked for do you use modeling for new designs before testing them in the lab? So maybe even not surprising, but it's looking like 53% are saying yes, only 8% are saying no, and the rest, the 33%, are saying sometimes. So what do you think about the results?
I'm happy to see that, obviously. I think that you know, modeling them and working with them is a good way to go. And I think it's definitely the trends of the future. So I'm excited to show some of the differences that our models might have compared to other vendors. So what do we put into our models? Well, we put physical parameters into our models. What does this mean? Well, this means that we put our fab, our processing parameters into our models. So we'll put our gate oxide thickness, our shielding thickness, our gate lengths, our shield thicknesses, our doping profiles. And so we'll take all those parameters that our process uses and put them into the models. We also add in the chip or the device floor plan. So we put in the size, we put in the gate runners, the pad widths, heights, locations, termination structures. And so we put all this into our models so that our customers are working with real devices in modeling. So you can see that once these are modeled over temperature, the outputs become very, very predictable. So we can measure voltages and currents. We can measure the body diode of these MOSFETs. We can measure RDS-ons, thresholds, and some more body diodes. In addition, we can measure very complex circuits that use capacitances. So you can see that this is the capacitance of a SiC MOSFET. And you can see, for example, the CRSS in blue here. It's modeled all the way from 0 to 1200 volts. And then you can even see the doping here. So when the JFET is pinching right at 8 volts, you can see that in the models. It's very, very powerful, and you cannot get this through just mathematical calculations. We can also put these models into switching applications. So this is a double pulse test at 25 degrees C and 175 degrees C. And so we can measure DVDTs, DIDTs, gate voltage transients. We can do switching loss, EMI, and we can study gate driver power loops. So this is very, very powerful information. But what I think is the most powerful is that this is very, very scalable. So for example, when we are developing a process, we can get models for our process months before our parts come out. Once our processes are set, or once we have our process inputs, we can now make these models work with customers so you can start simulating. And if you know what you need in your systems before you get the parts, and this can save a lot of time, and you can already know a lot of your performance attributes before you receive the parts. And this is very scalable to our charge, our QGs, our RDS-ons, and all of our capacitances. So this is very unique to us as ON, and this is a service that we offer to our customers at the design phase. So now we're going to jump into the main portion of this webinar, which is the silicon carbide solutions for electric vehicles. So the automotive market is moving to electrification, and there's a big global impact on this, which is about a 60% reduction in CO2 emissions. Another big thing for the semiconductor market is the costs that go into this. So for example, a combustion engine, there's about $30 worth of semiconductor content in those engines. But now when you're moving to plug-in hybrids and battery vehicles, you're talking about around $300 worth for vehicles. So there's a big increase in electrical content that's going into these vehicles. And just at an impact, we shipped enough traction modules last year in 2019 to reduce the CO2 emissions by 44,000 tons. And that's only going to increase. When you're looking at the vehicles, there's three main applications where these electronics are used. So we have the traction inverter, which we have solutions for IGBTs and silicon carbide. We have also modules for both IGBTs and modules for silicon carbide. Another place where silicon carbide is used is on the battery, so the onboard charger. We have power modules. Again, these power modules can be standard silicon or silicon carbide. And then we have all of our wide bandgap devices. And then another place where electronics are used and have been used now for several years is the 48-volt systems. So this is all your gadgets, infotainment, backup cameras, sensors that go around the car. So let's talk about the onboard charger. So the onboard charger converts the AC at a single phase or three phase into a DC voltage to charge high voltage batteries. These batteries are typically around 400 or 800 volts. So this is really the core system that takes the AC current, takes the voltage from your grid, from your plug-in, and puts it onto your battery. So they're used in both hybrids and full battery electric vehicles. They do the AC to DC conversion, so they do the rectification, and that's done in two stages. Typically it's done with a PFC and a DC-DC, so we'll walk through that. And size is probably one of the biggest constraints to these. They're big boards and they're heavy, and we need our electric vehicles to be lightweight, and so we have a very limited amount of space that we can use. So typically there's only 3.5 to 4 liters max for the size of these systems. Governments are definitely getting in, and silicon carbide allows bi-directional functionality. So we can already see that China is starting to impose laws that are requiring these systems to be bi-directional. Not necessarily in other parts of the world, but I believe as time goes on that they will start to require them too. These are relatively slow. Using your onboard charger is slow compared to a fast charging, which is an off-board charger. And these topologies are fairly well known. So PFC and DC-DC is fairly well known and are reusable. So they're reusable for the DC charging stations. And then where do we see silicon carbide? Well, the real benefits of them are seen in higher power. So when you're talking 6.6 and above, really over 6.6 is where you start to see silicon carbide and potentially GaN being involved. And then below 6.6 kilowatts is still where we're seeing silicon being used for silicon or superjunction and or IGBTs. Just walking through the different power and how long it takes. So typically an 11 kilowatt system will take about 10 hours on a single phase, and a 22 kilowatt will take about 3 hours on a 3-phase. So these would be your level 1, what they call level 1 and level 2 chargers, being a single phase and a 3-phase, and these are on the vehicles. So this is really used for when you are at your residence or lots of times at a work environment and you can plug in and you have a few hours that they're really utilizing the onboard charger. So taking a look at kind of building this up into pictures. When you charge in from your 240 volt or 120 volt from the wall, going to the cable, you're utilizing this onboard charger to then charge the battery. So these onboard chargers are made from either discrete components or APM, stands for Automotive Power Module, so that we can put some different topologies or some different things into these modules to make it easier. So what does that look like? Well, these are what we're making with the OBC. So here's a discrete design using discrete devices. You can see it's about 2.1 millimeters in area. And this is using discrete devices. Now when you move to power modules, OBC modules, you can reduce the size quite a bit. And then all these are packaged into a very nice looking box and put into the cars. So walking through the block diagram or how an OBC works is that you have your main voltage coming from the grid. You walk through a PFC unit, either single or three-phase. From this, you are rectifying the voltage into a DC voltage. From there, you need to isolate this through a DC-DC converter in order to charge the battery. So you need to isolate the current and the voltage and able to use it. Then that voltage goes to charge a battery. A majority of the batteries used today are lithium-ion batteries. This means that we need a BMI battery management system in place to look at the charge and making sure that all the cells in that battery are being charged equally. This is then communicated to the control unit. This is where the processor is, and then this feeds back into our either the DC-DC stage or the PFC stage. A couple of different topologies that are used are interleaved or voltage source inverter. If we're moving to the bidirectional, then we're looking at more of a Vienna style or a totem pole are being used today. And then we have our DC-DC isolated, which are bidirectional with a full bridge or half bridge. Typically an LLC is the most common, or a zero voltage switching control, a ZVS. So power factor correction is a very important part of this, and it's because when you plug your battery, when you plug your cable into the wall, you are going to get a displacement factor. So this displacement factor is the difference of when you plug in and you start up, you have a shift here on your sine wave. So the PFC, what that does is this changes this and it matches your current and voltage to match. In addition, you have a distortion factor. So this is your signal. So your signal can be very tiny or very big. It's distorted. And so what the PFC does is it matches the distortion factor and the displacement factor to create one to be matched. So walking through this in a little bit more detail for the power stages, the PFCs that we have coming off a three-phase system use three-phase half-bridge MOSFETs. So these are a three-bridge with 1200 volts. These then switch and then put a DC voltage onto the output. That DC voltage is then taken over by the isolated LLC converter. So here we have a full bridge. That full bridge is then sent through our transformer, and then we have a full bridge diode, SiC diode rectifier on the output phase. This is for unidirectional, so this is one way. If we change these to MOSFETs, then you get bidirectional charging. The output here that's what is then used to charge the battery. So the results of this, so for three phases at 11 kilowatts, you can see here the green is the state of the charge. So this is essentially monitoring the battery. So starting here at 0 and moving to 100% takes right around 3 hours to charge a 400-volt battery pack. And we're doing this, so this 400-volt battery pack, we're doing this right at around 96% efficiency. So these are both stages combined about the highest efficiency that you can get. Now, each phase is higher, but then when you average them, it comes a little bit lower. And really, silicon carbide is really the highest efficiency that you can get on these higher power systems. We have a whole portfolio of onboard chargers on Semiconductor, both single phase and three phase. And so a lot of the smaller ones, the 3.3, 6.6, are made with silicon, and they're a little bit smaller, mostly for the hybrids, so you're not running off of a full battery. But when you get to the full battery, the full electric vehicles, this is really where we turn over to silicon carbide, three-phase higher power systems. So the one that we have released that customers can order and that they can use and that we can provide all the design files for is right here. But we're also making an 800 one for an 800-volt battery. So this was for a 400-volt battery. And then we're also doing our bidirectional one as well. So we have a bunch of support and collateral. Again, presentations, design documents, we have notes, we have these landing pages, and we have these boards available for purchase, so they can even be purchased and tested in the lab. Okay, so now let's move over to the drive system. Once our battery is charged and we have a charge on our battery, we need to drive the vehicle. So we take the voltage from the battery, we have to run it through an inverter. So this is a traction inverter, which then drives the motors. There are various powertrain configurations that can be done, but there's two main motors that are used. So we have an AC synchronous motor that's typically seen on more of an economy vehicles, and then we have an AC induction motor. This is a performance motor. And just a few of the differences, so for your AC synchronous or your economy motor, they have a magnet right here, so it's placed on the rotor. It doesn't allow the motor to slip. And so if it doesn't slip, it allows it to run more efficiency at lower RPMs. So these motors are typically found on the back wheels. They are 150 kilowatt motors, and they have about 310 Newton meters of displacement. Well, our AC induction motors use a coil. So you can see that they have coils here on the rotors, and when you power them, they produce slip. The slip can be used to create maximum torque. So it's the twisting force through your RPMs, and this can boost basically the performance and add additional power to the drivetrain. So our solutions for our traction inverter is we have a VE-Trac, so this is vehicle electrification of the traction. And so we use these modules right here. These are single phase half-bridge modules. We put them into a cooling system or a jacket, and we put 3 of them for our 3 different phases, and then we can attach them to our control board. So this is the driver that drives these modules, and we have full development kits. We have full development kits available today with IGBTs, but we're also creating these kits for silicon carbide as well. And it's one of the advantages of this module is you have one power module for many different power levels. What this means is that you can take a 3-phase system, but you can also parallel them. So you can create a parallel and you can get over a 200% increase in output power. So this 150 kilowatt motor now can be a 300 kilowatt motor just by simply adding another sleeve and paralleling them in parallel. So it's very, very scalable and very attractive to a lot of customers that are designing these power inverters for electric vehicles. So just looking at how a traction inverter works. So again, this is the battery. You have 3 phases. They are 3 half bridges. So we're using our MOSFETs. They are connected in a half bridge configuration, so a high side and a low side. Those are then connected to the motor. So this, once the voltage is here and you start switching them, you are creating an AC current. So this current then drives the motor, so with pulse width modulation, so you're putting an input voltage on here, and motor control, really you can now control these output across the windings and the motor and drive that motor. So what different manufacturers can do is they can change this AC current, both the frequency and amplitude of it, and that will change the speed and torque and performance of your vehicle. Another really nice feature that the traction inverter allows is regenerative braking. So what this means is that when you take your foot off the pedal, you can create current and voltage and take that back to the battery. So how this works is that when the motor is running, you're creating a voltage. This voltage is modeled here. And when you take your foot off the brake, for example, when you close one of these switches, then now that is connected to ground and it starts braking the vehicle because it's not running. That voltage is then stored across this inductor onto this node, and essentially now we have a loop where we can take that voltage back and start charging your battery. So this is a really nice feature because instead of using disc brakes, you can just take your foot off the pedal and the motor itself is slowing your vehicle down, and then you are putting a loop back where you are charging your battery. And so looking at the performance difference between IGBTs and silicon carbide, you can see that you get about 3 times lower switching losses using silicon carbide over IGBT. So this is your turn on energy, your E on, and your turn off, your E off energy. And so you can see that it takes less energy to turn on and turn off these devices. And what that ultimately means is that when you are driving a vehicle, and if it takes less energy, that means that you can drive further on a battery. So that gives you basically more miles per battery, and it allows you to charge less and go further, and then it's also better for your battery. It stops the degradation of your battery from happening. So lastly, we're going to look at the charging infrastructure. So if you're not wanting to use your onboard charger, then we have what we're creating is DC fast charging. And when you plug these in, basically this can charge the batteries themselves. So currently there's 2 levels for DC chargers. That is a 44 kilowatt system and a 250 kilowatt system. A 44 kilowatt system can charge your battery in about 30 minutes. And what we're really looking for is, in these very, very high power systems, is to charge your battery in about 5 to 7 minutes. So this would be more comparable to refueling your vehicle at a gas station. So the charging infrastructure is very broken up. It's really being driven by a lot of governments, and governments are kind of being involved, and it's not clearly defined how the charging infrastructure is going to grow. Tesla, for example, took a lot of ownership in that, and so in order to utilize driving a Tesla, they put their own charging stations in place. So as a lot more of these companies come out, it'll be interesting to see if they follow that same idea by creating their own, installing their own charging stations, or if they're going to leave it up to others to start charging them. But a majority of these existing stations are level 1 and 2 still. So for example, at like workplaces, or if you're going to maybe like a grocery store where you're going to be in there for 30 minutes to an hour, they're still using level 1 to level 2. So they're not fast charging. And I believe from a consumer's point of view that we want the equivalence of refilling our battery or charging our battery like we're filling up at a gas station. So I think the demand for the DC charging infrastructure is really going to be starting to grow as more of these vehicles are coming online. And so as the power increases, so is the need for silicon carbide. And so what we'll look at here is these are two different charging poles, so it's different charging stations. This is using IGBT solution. This is using a silicon carbide solution. We see a 10 times smaller in terms of size. We get 60% less power draw from the grid, and we can achieve a peak efficiency much higher because we can make much bigger systems. And so now here we're using a 3-phase Vienna PFC. So this is Vienna. Typically we're putting these into some power modules. And then of course we have to go through our DC-DC, our isolation stages. And then we have our battery voltage sitting right here, which can then charge the battery directly. So we can bypass the onboard charger. So now we'll walk through what does ON offer in terms of our silicon carbide devices. But first, another question for everybody. Are you currently using silicon carbide components in your designs today? So yes, no, not yet, but planning to use them in the future. I think over the past few years, as the hybrid vehicles came out, there wasn't as much of a need for silicon carbide because they were able to get that lower power rating, like 3.3 and 6.3 kilowatts to charge those batteries very easily. But as the trend is moving to full electric, I definitely see the silicon carbide as going to be needed. That's really what's enabling us to go to full battery. Without the silicon carbide, it would not really be able to enable the full vehicle, the full electric vehicles. Looks like we have a few seconds left.
All right, thanks Brandon for asking the question. So I have the results for your question, are you currently using silicon carbide components in your designs? So I'd like to think that some of these answers are actually because of the presentation you just gave, because it looks like 29% are saying yes, 27% are saying no, but the leader is 38% saying not yet, but planning to use them. What do you think, Brandon, about the results?
Yeah, well, like I kind of said, I think that previously, you know, the hybrid vehicles, we didn't really have as much of a need for silicon carbide, but now that we're moving over to full electric vehicles, you know, you'll really need to use silicon carbide in order to be competitive and to create vehicles that people are going to want to drive. So I think that's very interesting and a very good trend. So ON offers a very wide and very big portfolio when it comes to silicon carbide. So it's a very big eye chart, but if we break this down, the first portion right here is your silicon carbide diodes. So we have 650 volt, 1200 volt, and 1700 volt diodes. We have these in a number of discrete packages. And then now we're able to take those devices, so those diodes, and we're able to put them into modules. So these are called hybrid SiC modules. they have an IGBT with a silicon carbide diode in them. So we have a couple of these that are going to be released for automotive, but these have been released now in the industrial segments for a couple of years. Likewise, we have a wide range of silicon carbide MOSFETs here at the bottom. So we have 650 volt, 900 volt, 1200 volt, and 1700 volt MOSFETs that we have. Our 1200 volts are all released. We have 900 volt discretes released. We are sampling right now our 650 volts and our 1700 volts. And then we take those die and we put them into full SiC modules. So this has either just all SiC MOSFETs, or it can include some silicon carbide diodes depending on the module. And these are really for all industry, but these are really coming out towards the end of the year. So we've been very engaged with customers over the last 2 years with our modules, and now these are going to be here, a majority of them released. We also have already released them for the industrial market. So taking a quick look at what our OBC APM module platform looks like. So as you saw in the onboard charging slide, you saw that a discrete solution was quite a bit bigger, about 40% actually bigger in size, 2.71 millimeters squared compared to 1.5 millimeters squared by using our APM. APM stands for Automotive Power Module Platform. So we have 650 volt and 1200 volt modules available at a varying level of complexity. So you can have low complexity or high complexity. And what these complexities lead to is a bunch of different topologies. So in these modules, we can do a half bridge LLC converter, we can do a buck boost, we can do bridgeless, we can do interleaved, and we can do dual active. So we can put all these power stages into our modules, which reduces the size and actually increases the performance. It's better for your heat sinking, it's better for the weight. And so we're really getting a lot of traction and a lot of engagement with our customers using these modules. Likewise, for our electric vehicle PIMs, so our traction modules, we do have a 6-pack. So this is that 6-pack where you have your 3 phases of the traction module all into one module. So this is really what we call plug and play. And we have that again at 1200 volts and at 900 volts. And then we have what we call our scalable platform. This is where we have, this is our single phase half bridges. We put 3 of them. We can create really nice cooling jackets, and we can scale the power on these very, very easily. We are creating these in both 1200 volts and 900 volts as well. So I wanted to conclude this webinar with a few comments. So really what we're seeing in the market, in the car world, is that we're seeing that the combustion engines is reaching its peak for manufacturing output. And we're actually seeing that year over year, the forecast is a decrease. So the electric vehicles are estimated to have about 25% share by 2024. Silicon carbide plays a very important role in charging the batteries and driving the motors. Really, we're looking for more power, higher efficiency, and that enables us to drive further. And ON Semiconductor is a key supplier of silicon carbide, and we really, one of our advantages is we have a full ecosystem of modeling and device support. We have great application support, and we have a lot of material, a lot of demo and evaluation boards that can be utilized. So please, if you have any questions, visit our website, reach out to any distributors or reach out to local sales, and we would love to help you more. So with that, I'd love to take any questions that might have come in, and I'll do my best to answer them at this time.
All right, thank you, Brandon, for the excellent presentation. So during the presentation, we received a number of questions here, so I'll just jump right in asking them. And as a reminder to everybody, if you would like to submit any questions, please open the Q&A window on the right side of your screen and send your questions to all panelists. So the first question that I see here, Brandon, at present, most mainstream SiC manufacturers are claiming to do the entire industry chain of SiC. What's ON Semiconductor's consideration?
Yeah, so there's a big process, a big supply chain for silicon carbide. From a device level, it starts at the substrates. You have to add epi, you have to go through fab, then you have to do your packaging and all your testing. And so ON is definitely working towards full internal supply. Currently today, we have everything internal. The only thing that's not in production yet is our substrates. We are looking to be in production over the next 2 years with our internal substrates, but we already do everything else in-house. So we do our own epi, we do our own fab, we do our own packaging, and we provide all the testing. So some suppliers have that all internal, others don't, but I think for the future that is very important, and ON is definitely key on getting having a full internal supply chain.
All right, thanks, Brandon. So the next question I have here, does the SPICE model include dynamic thermorealistic effects based on Foster or Cower models and linked to external heatsink temperature?
I don't know the specifics of those models, but it does do thermals. So we do have our theta JC and our thermals. It does model thermals. So how it does to your heat sink and some of those other models, I'm not 100% sure, but I know that our models do model thermals as well from the package. So the package is included, and then it does provide thermals for that model.
Thanks, Brandon. So the next question, is the Vienna PFC unidirectional unless you have many active switches?
So the PFC Vienna using silicon carbide is bidirectional. Of course, you have a non-isolated DC on that. So you still have to go through the isolation stage, and that isolation stage also has to be bidirectional. So you have to have your both power stages bidirectional in order to go both ways. But the Vienna PFC portion using silicon carbide is bidirectional.
Thanks, Brandon. So the question we have here, we are talking about EV adoption in SiC, but is there also an opportunity for hybrid vehicles?
Yes, I think there is, but it depends on the power levels. So typically, those batteries are much smaller, and so they still have a combustion engine in them, and then they have the battery. And so when you typically, like if you're sitting on a stoplight and you start, it starts on the battery, and then it maybe converts over to the engine. And so the batteries just aren't quite as big, and so they don't need the high power levels in order to charge them. And the drivetrain is still kind of working off of an engine. So it can, but then the factor comes into cost. So when you're building up the car, cost is very, very important. As the more electronics you add, that increases the cost of the car. So OEMs and manufacturers are really looking at the cost very closely. So to answer the question, yes, they can be used, but is it really necessary to use them? We don't see that quite as often compared to the battery electric vehicles.
Thanks, Brandon. And just a reminder to everybody too, if you want to submit any other questions, please click on the right menu bar. You can click on Q&A, and then you can submit your questions there. So the next question we have is also related to hybrid vehicles and the hybrid market. What does the hybrid market look like in terms of ICE and EV?
Yeah, so as I mentioned, typically a hybrid, the main thing of a hybrid has an engine and a battery. And so from how I know that they're used is typically at lower speeds or like sitting at stoplights and then starting, it uses that battery. And then when you get up to higher speeds, typically it has to turn on that engine. So if you're driving down a freeway per se, or if you're just driving in town, it tries to use the battery as much as possible. And then when you have to go faster, it converts over to the engine. So from the market, I think that the hybrids will still be manufactured, and that is included. By the way, the hybrid is included in that 25% market share. So hybrids are definitely not going away. I think that they're going to increase, as well as the battery vehicles, full electric vehicles, are going to increase.
Thanks, Brandon. So I have a two-part question here for you. So the question is, do you only have LLC full bridge designs or phase-shifted full bridge, which is less efficient but easier to control? And the second part is it worth the pain using LLC instead of phase-shifted?
I'll have to look at exactly what we have. I don't believe that we have phase shifted released right now in a module, but I would have to look at that. Both parts of these questions, I think it would be better to write them into a local FAE or distribution and go through so that we can look at it in further detail. Our modules, we have a lot of different combinations of them, some of them, and so I don't have every single part number memorized. So I think that's a good question. I think it's definitely something that we can support, but we would like to channel that question through our field.
All right, thanks, Brandon. So the question here, I did not see what was the max average current of your SiC diodes for what they can handle. Can you tell us what the maximum average current is that the components can withstand?
So for our MOSFETs, we have currents that range from 10 amps to over 100 amps. So some of our 1200 volt MOSFETs can take easily over 100 amps of current. And for our diodes, we have a variety of diodes ranging from 5 amps to 4 amps, all the way up to 50 amps on our diodes.
Thanks, Brandon.
And all of our products can be seen on our website that are released as well.
Thanks, Brandon. So the question here is, how is the battery life affected if we go for level 4 chargers and charge them in less minutes? And I assume this is for full electric vehicles.
Yes, yeah. So interesting. So one of the things that we have to monitor is we have to monitor the current. So your power is voltage times current. So that is definitely one concern, is because we cannot pump a lot of current onto these batteries, because that will degrade them and that will deteriorate them a lot quicker. So that's why different vehicles will allow for different power levels to be used when you plug in. And so that's another reason why they're moving to an 800 volt battery. So an 800 volt battery, you can charge at a higher voltage while keeping your current lower. And so, but that is something that will need to be solved. And the way that it's going to be done is by controlling the current.
All right, thanks, Brandon. So here's a question on the main inverters. So what are ON Semiconductor's SiC adoption in the main inverters?
So our adoption is, we have shipped, I don't remember how many, but we've been shipping them already in production since last year. So 2019, we've been shipping them. Those are typically IGBTs right now. And our Silicon Carbide modules are coming out at the end of the year. So they're already designed in multiple electric vehicles. And So it will be very interesting. I think it was how it was a share, but the adoption of it will start to increase every year. So we have to kind of wait till the launches of vehicles come out in order to see that adoption. But I can tell you that every single ODM is really involved in electric vehicles, and we are engaged with, I can probably say, almost every single one. And so the adoption will definitely start coming out as more and more models come out.
Thanks, Brandon. So I have here a two-part question. The question is, will SiC eventually take a backseat to GaN? And then where's ON's positioning in GaN?
So I think that GaN and SiC are, I don't think that silicon carbide will take a backseat to GaN. I definitely don't believe that. GaN, really the max voltage GaN can go is right around 600, 650 volts. The lowest silicon carbide can go down is right around 650 volts, and it goes up. So for higher power, GaN will not replace SiC. There is 650 volts, though, where GaN is an option or SiC is an option. I think right now, people think that GaN is a little bit cheaper than silicon carbide, which it is, and so that is where the big growth is going to come from. I can tell you that GaN is a very tough device to drive. It's a very sensitive device, so you have to have very advanced design with GaN and to be able to control it. And so I definitely think that it has some advantages in some systems where you want to increase the frequency. It can definitely go a little bit quicker than silicon carbide. But my personal view is that GaN will not grow at the growth rate it's been projected. GaN was supposed to take off 10 years ago. It never has. And so I still think that there's a lot of optimism around GaN, but the reality is that silicon carbide is a much better proven solution, especially around some of these power levels. The second question is, where does ON Semiconductor stand in GaN? We do have GaN. We have internal GaN. We are working with select customers on our GaN, but really one of the things that we're focusing on around GaN is the packaging around GaN. If you look at GaN today, it's in a bunch of different packages. It's kind of all over the map in terms of CSP or wire bonded or package sizes. Nobody has the same strategy. So our strategy is really working with customers that we want to work with and developing a package that you get the best benefits of GaN out of.
Thanks, Brandon. So the question here is, can the SiC drivers be integrated into the same package as the FETs to save space and hopefully cost?
Yeah, so that's something that we are looking at, so integrating them. One of the issues it comes as where you're getting the high voltage from off your board, so what you're coming into, and the drive loops are not quite as sensitive to having it internal, but that is definitely something that we are looking at, is bringing the drive into the same package, and then and doing the half bridges in there. So we actually do have that. It's called an IPM, an Intelligent Power Module, and we do have some actually right now for the industrial market. So we are looking at that also for the automotive market.
Thanks, Brandon. So the next question, are there any drawbacks in using SiC MOSFETs, which are very fast devices, for power inverter motor driving, such as high DVDT and partial discharges?
Not that I can think of off the top of my head. The high DVTs and stuff, you just have to be able to control your overshoots. So as I talked about, one of the points that we pay attention to is the ruggedness. So the ruggedness of the device says, if you're going to switch them quick and you have overshoots, how does it handle that? And you want to make sure that you're not breaking down any of the oxides in the gate. And so on our Gen 1, for example, we have a max rating of 25 volts, but we test the gate oxide up to 40 volts in reliability. So we have quite a bit of margin and protection around that, and so I don't see any drawbacks switching devices quickly.
Thanks, Brandon. And just to note, so everybody, we are at time in case you have another meeting you have to get to, but we will continue and keep the meeting open to answer questions as they come in. So the question here, do you expect the drastic adoption of high battery motor voltages in EVs to push the market of semiconductors to create components with higher and higher voltages?
So I'm not as involved in the motor world. So these high voltage motors, typically these, I'm not 100% sure. I can't really answer that knowledgeably, but I do know that silicon carbide can go up to, there's silicon carbide that can go up to 3.3, so 3,000 volts. I know that it could probably go up to 5,000 volts. So if the motor voltage increases, the silicon carbides can definitely match that, and it already can match the higher voltages.
Thanks, Brandon. And now a question about temperature. Can SiC operate at 200 degrees Celsius for downhole drilling applications?
So yes, so silicon carbide, the device itself can actually operate well beyond 400 degrees. The limiting factor becomes your packaging. So using a plastic, using a molded package, it becomes the package itself that becomes a limiting factor. And we are looking at materials in our package to rate our devices at 200 degrees C operation. So yes, they can be used. The limiting factor is the package, and we are working on packages that can operate at 200 degrees C.
Thanks, Brandon. So the next question, is trench for SiC on the radar, and what's ON's approach and the differences of ON's approach for trench for SiC?
Yes, good question. So we do have a trench program in process, and in terms of what our approach is, I can't share that on this webinar, but trench is on our roadmap and being worked on.
All right, thanks, Brandon. And just the last question that we have here then. So beyond electric vehicles, does ON Semiconductor plan to extend SiC to even higher voltage for other applications like used in train?
Yes, so we do. We have 1700 volt SiC MOSFETs that are sampling. Above 1700 volts, you're talking about like 3000 volts. That's not an area that we're looking at right now. But higher voltages such as 1700 volts is an area that we are looking at.
All right, thanks, Brandon. And thank you again for everyone for asking your questions, and Brandon for answering them, and for the excellent presentation. If we didn't get back to any of your questions here live, we'll follow up through email at a later date. So on behalf of ON Semiconductor, I would like to thank everyone for attending, and thank you, Brandon, for the excellent presentation. Have a good day, everyone.
Thank you so much.